Hello! In this video we're going to look at some word problems, and we'll look at several different kinds of word problems throughout the semester. So this is really one particular kind. So before we get to what they're called and some strategies for solving them, I wanted to show you an example of what one looks like. This is a pretty easy example. So we've got this description here describing something that's going on. One important thing about these kinds of problems is that we have some question here about a rate of change. So it's asking us about a rate of change. That should help you think about a derivative. And then the other thing that we're given is some information about a radius and also how that radius is changing. So we have some information about what the radius is and how it's changing, and we're asked about how some other variable changes. So these kinds of problems are called related rates problems, basically because that's what they are asking you to do in the problem. I'm given some information about a rate of change, and I'm asked to find some other information about a related rate of change. Okay, so I have some suggestions for how to tackle problems like this. We're going to scroll up and look at some of those steps and guidelines for tackling problems like this, and then we'll come back and do this example. Okay, so here are some of my suggestions for how to solve a related rates problem. So first of all, you want to make sure that it is a related rates problem. We talked about some of the key parts that we would be looking for in a problem that would make it related rates. It describes something about rates of change and asks us about something about other rates of change. All right, so when you read the problem, one important thing to pay attention to is that it often describes several different numerical quantities. Sometimes some of those are fixed quantities. So those would be things that don't change. So if there's anything in the problem that doesn't change, you can just plug that number in at the very beginning. If there are other things in the problem that do change, you don't want to plug those numbers in right at the beginning. You need to treat those things as variables. So variables would be things that change. And then the other important part of the problem is that they will often describe some things that are rates of change. And so they'll tell you something is increasing at a particular rate or decreasing at a particular rate. And what that really represents is a derivative. Okay, so rate of change is a derivative. All right, so read the problem, identify all that stuff. Sometimes there are geometry problems, and so you might want to draw a picture if that's appropriate. My biggest suggestion, though, for getting these problems started and tackled okay is to organize the information about the variables and the rates of change in a table. So I'll show you how to do that with the example problem we were looking at, and then I'll use that strategy in all these videos that I'm doing here. All right, once you've organized all the information in the problem, you need to find an equation that relates the variables in the problem. So sometimes that's easy, sometimes that might be given in the problem, and sometimes that's a little hard. You may need to look up some geometry formulas. There is a handout in our class notes or in our class website that has some geometry formulas. So you might need to look up some of those. There are other problems that might relate to formulas from physics or chemistry. Those formulas might be given to you, or you might look them up if you're in a physics or chemistry class. Okay, so once you look up those formulas and think about those formulas, then we're going to use implicit differentiation. The rates of change, the derivatives that are given, are usually given with respect to time. So because we have those rates of change or those derivatives that are given usually with things changing with respect to time, we're going to differentiate through the equation with respect to time t. That has to do with the fact that we're given rates of change with respect to time. So if you remember the example, it talked about the radius decreasing at a particular number of inches per minute. So the rate of change is this derivative. Usually given with respect to time, which is why we want to differentiate with respect to time. Okay, once you've done all that, then at the end it's pretty straightforward. You're just going to substitute in values for the variables and rates that you were given. Once in a while you have to do a little extra work to find some of the numbers that you're going to need to substitute in, and then at the very end you're just going to solve for whatever rate you're supposed to find. One important thing that I will always ask you to do is label your answer as a rate of change using appropriate units So we'll pay attention to the problems and the variables and what those are so that we can organize that and think about how to label our answers. Okay, so let's go look at the example we had, and we'll kind of follow these guidelines and think through that problem. Okay, so here's the problem we were looking at. It tells us that we've got water evaporating from a circular shaped puddle. So we've got some kind of circle involved here. Maybe I'll draw a picture of a circle. We're assuming the puddle retains its circular shape, so we always have a circle. And it asks us some information about an area changing. All right, so we've got some information here about variables and those variables' rates of change. The first thing that it talks about there is area changing. So area is one of my variables, and it's asking me to find an area rate of change with respect to time. So I'm just kind of setting up this table. It's talked to me here about area. I'm supposed to find that. The other variable that it talks about in the problem is radius. We're given a particular value for the radius at a particular time that we're interested in. When that radius is 9 inches, that doesn't stay fixed. That is a variable. It changes, so the radius doesn't stay 9. It's a variable. And then I'm going to just kind of complete my table here. So the way I usually organize these tables is just listing the variables and their rates next to each other. Sometimes that information is given in the problem. Sometimes it's what they're asking you to find. And sometimes you may or may not need actually all those values in the chart. But this just kind of helps keep everything organized. So for each variable, I've got a rate of change labeled over here. Okay, so in this problem, we're given some information. We're supposed to find at what rate the area of the puddle is changing. So that's what we're supposed to find. When the radius is 9 inches, I already filled that in, and the radius is decreasing by 0.3 inches per minute. All right, so that's a rate of change for radius. One important thing here is to note that the radius is decreasing. So that is a negative rate of change for that radius, 0.03, and that is in inches per minute. The units on that would correspond to whatever radius is per unit time, whatever the units of time are in this problem. Okay, so that's the information that's given in the problem. I don't have a value here for A, and maybe I'll need it, maybe I don't. So that is the read the problem, organize the information into a table step that I suggested. All right, the second main step for solving problems like this is that I need to think of an equation that relates the variables. So I need an equation that relates area and radius for a circle. So maybe you look that up. Hopefully this is one you know, but you look up or you remember that area is pi r squared. That gives the area of a circle. All right, so that's the equation I need that relates the variables in this problem. I'm now going to take that equation and I'm going to differentiate implicitly with respect to t. So I'm going to differentiate both sides of the equation with respect to t. So I'm treating both a and r as functions of t. All right, so when I do that on the left side here, I'll just have 1 dA dt. On the right side of the equation, the pi is a constant, so it'll just come along. For the r squared, I'll bring down that exponent and subtract 1, so 2 pi times r to the first. But remember, we're differentiating implicitly and treating r as a function of time. So I have this extra dr dt factor here. This is just like when we use implicit differentiation. Okay, so the 3 first steps that I listed were organize the information in a table, draw a picture. We did that. Find an equation that relates the variables. That was our a equals pi r squared. And then differentiate implicitly with respect to time. So we've done those first 3 steps in those suggested steps. All right, the 4th step is then to substitute in the values for the variables and rates of change that you're given. Hopefully you don't have to do too much extra work. Let's see, if we look at this chart, this is when that chart can be really handy. The dA dt is what I need to find, so I'm not going to substitute anything in for that. R, it's given me a value to substitute in here. I'll substitute in r equals 9. And we're also given a value to substitute in for dr dt. So we'll substitute in negative 0.03 for dr dt. All right, and that's everything. So then we should be able to find our dA dt. All right, so let's see, I have dA dt equals 2 pi, my r was 9, and my dr dt was negative 0.03. Okay, so I'm going to go ahead and simplify that. I might take 2 times 9 times negative 0.03 and write that as negative 0.54 pi. That would be in exact form with the numbers that I was given. If I want a decimal approximation, I can type that into my calculator and get a decimal approximation. So I'll get about negative 1.696. And then I want to make sure that I label my answer using proper units. So to think about the units, I want to think about the rate of change that I'm supposed to be finding. So the rate of change that I'm supposed to be finding here is my dA dt. And if I just think about the units that A would be measured in, A is area, and my distances here are measured in inches. So the area would be in square inches. And T in this problem, the time, is measured in minutes. So the appropriate units on my answer here are square inches per minute. If I just pay attention to the units on my derivative, that tells me how to label my answer. So whether I label that in exact form or decimal approximation. When you do the online homework, sometimes it asks for exact form answers, sometimes it asks for decimal approximation. When you do other homework that you're going to turn into me, you should pay attention to what the instructions say, decimal approximation or exact form for the answer. Okay, so we'll look at some more examples, a little bit more difficult examples in some other videos, but this is basically the idea with these related rates problems. The key part is organizing that information into a table. That will really help you. All right, watch some more videos on it.